I hope you all have been having an amazing day 4 of the Python Web Conference. I know I have been. There's been some amazing talks today. I really enjoyed our keynote this morning. And our keynote coming up is Guy Royse. I'm so excited to be joined by Guy today. I'm going to go literally grab some Scooby snacks so I can sit and enjoy them while I am watching your talk. I will let you take it away.
Well, Jinkies, thanks. Is this the part of the talk where I should give my obligatory I can impersonate Scooby-Doo? Maybe. So I'm going to share my screen here so you all can see my slides. That's kind of important. So welcome to my talk, Mystery Machine Learning. My name is Guy Royse. I'm a developer advocate at Redis Labs. And that's pretty much all that matters on this slide. I always appreciate a follow on Twitter here. So if you are so inclined, give me a follow on Twitter. And of course, the code for this, all my code for all the code things are going to be at github.com/Guy Royse. And if you want to read my outdated blog, you can go to guy.dev. And I got to talk today about recurrent neural networks. And before we go into that, I want to point out one really, really important fact. And usually this is an interactive audience bit here where I say, what do you think this stands for? And then everyone puzzles on it for a while. And then someone finally lands on that it stands for, I am not a data scientist. And then I give them a t-shirt. We're not in person, so I can't do that. But the lesson or the warning here is the same. I am not a data scientist. I'm going to talk about recurrent neural networks and those sorts of topics. I'm going to talk about data science topics. But I'm a developer. And I've been writing software for years. And I'm a fan of data science. And so what I do is I go out and I learn about different data science topics as a developer, and then I sort of translate them into, I'm going to say developer speak. I think about them as a developer because I am a developer. And so I build talks to share what I've learned with other developers. And so what this means is you get a good developer's perspective on how some of this machine learning stuff works. And at the same time, we have someone who is in some ways an expert speaking outside of their field. And so there are lots of nuances and details that if you're a seasoned data scientist, I might miss. But I try not to go so deep as to make those an issue. And I also try not. I don't claim to be a data scientist or an expert here. So this is my big caveat in front of all my data science talks that I give. So in addition to not being a data scientist and being a developer, I'm an enormous fan of Scooby-Doo. Scooby-Doo, where are you? Scoob would come on and he would do his little laugh. And it just give me a little happy feeling when I'd hear it. And I've been watching Scooby-Doo like I think most of the world since I was a kid. I watched it back in the 70s. And the thing I always liked about it was that you had this supernatural thing, this thing that appeared to be supernatural, mystical, hard to understand, right? And it became, turned out the ghost was just a man in a mask. And that gave us, I don't know how I want to say this. It made something that was mysterious, mundane or knowable. And I kind of like this analogy to machine learning. Like when you look at machine learning, we kind of look at it as almost a magical process where I put magic numbers into here and the model just figures stuff out somehow. But that's not how they work at all. They're 100% deterministic. We tend to personify them, but they're 100% deterministic. It's just doing math. And so there's not really any mystery to how they're working. And so we're going to go in and we're going to dive into the details of how some machine learning models work. We're going to look at recurrent neural networks specifically. To do that, we're going to build a fun and rather ridiculous application. What we're going to do is we're going to take the lines from Scooby-Doo, from the movie and from the cartoons and various Scooby-Doo intellectual property over the decades. And I've got a simple data file. It's got whether, who from Mystery Inc. said it, Shaggy, Scooby, Velma, Daphne, or Fred, and the line. So that's the entire data set. We're going to take that data set and we're going to build a model that will tell us who said it. If Roque Raggy, that's probably Scoob. Jinkies, that's probably Velma. So we're going to build a model that knows how to do that. We're going to deploy that model onto Redis so that we can make inferences against it. And then we're going to build an application that consumes that model on Redis and it will tell us whether it is Daphne, Fred, Scooby, Shaggy, or Velma. So that's what we're going to build. In order to build this, we're going to cover the following topics to build and understand it. We're going to cover the basics of neural networks and maybe a little deeper. I'm going to go fairly deep into how neural networks work, not how they're trained, but how they work once they're trained. And then in specific, I'm going to go at how recurrent neural networks work. Recurrent neural networks are a special type of neural network that is good for handling time series types of things, or things that have a natural order, whether that's chronological or some other type of order. We're going to use Keras to do this. And so we're going to talk about what Keras is and how we can use it. And then we're going to run this on Redis. And so we'll talk about how we can deploy our machine learning and AI models to and deep learning models to Redis. So let's look at neural networks first. What are neural networks? Well, you've probably seen this picture before. It's a little picture of a neural network. It's got an input layer where we put in this example, 4 numbers, x0 through x3. It has a couple of hidden layers, and it's got an output layer where our answers are at. And each of these layers flow into each other. And so we put in 4 values and we get 3 values out by flowing through these input layers. And the idea here is that these input layers are sort of posted or pegged at a particular value, and then these ones will transform it in some way and pass it to each layer, and then each node to the next layer, which will transform it in some way, which passes it to the output, which will transform it in some way, and we'll get an answer. And so this is sort of these layered transformations that are happening. But the net result of this neural network is ultimately it's a function. And when I say function, I mean function in the mathematical sense. You put some numbers in, you get some numbers out. And ultimately, functions in mathematics can be used to draw lines. And so we could draw a line on a graph here. You know, our neural network might draw a line that looks like this. And then we can use those lines to make to understand things about the inputs. We could use those inputs for classification to say, is it one thing or another? Is it a hot dog or not a hot dog? And if it's on one side of the line, it's a hot dog. And if it's on the other side of the line, it's not a hot dog. And the further it is from the line, the more sure we are that that's the correct answer. So that's one thing. This is how we classify using these functions. And we can also predict discrete values, or not discrete values, sorry, continuous values by picking a point on the line. So if we put in our x, we can then find where it intercepts with y and get our answer. And so here we could say, we got a little chart here, a little function that will tell us how many Scooby snacks are required to overcome a particular spookiness level. So, Scoob and Shaggy aren't necessarily going to do it because it's scary, but, if it's, they can overcome their fear with the proper incentives. And so, we can see here that we got, would you do it for 2 Scooby snacks? And so if we look at the spookiness level of 2, that's our X, we can predicts Y, that it would require 2 Scooby snacks. So this is predicting a continuous value. And this is ultimately what machine learning does, is it's drawing these lines and either picking a number on them or looking on either side. To understand how a neural network does this, to how a neural network is a function, let's look at the individual pieces of a neural network first, the neurons. This is the smallest unit within a neural network, a simple neuron. We're going to take the simplest neuron we can. We've got a neuron that takes a single input, not multiple inputs, just a single input, an X, and it outputs a Y, which is our single output. And so you can see here how this can draw a line, right? You put in all the values for X, and it will draw a line for all the values for Y. Inside of this neuron, we have 2 values that we're going to talk about here. We've got the weight, which weights the input. So we weights it by multiplying it. So we take X times W. The input times the weight, and we have a bias, which we add to that product. So we multiply the input times the weight, we add the bias, and that gives us our output. And so here's what's going on in a neuron represented as a formula: our input, our weight, our bias, and our output. Now, if you're astute and took high school algebra, you might recognize this as being another formula. good old y equals mx plus b. And in fact, all we've done is reverse the formula and flip the w over, right? it's almost all the same letters and everything. Now, here m is the slope of that line. It's how steep or how gentle that slope is, and b is the y-intercept. It's where that line intercepts the y-axis. And so a neuron, an individual neuron, just draws a line, and that line can be, steep or gentle. It can be far to the right or far to the left. There's a lot of options, right? But ultimately, it's just drawing a line. But sometimes you want a neuron to do something that's a little less linear. You don't want just to draw a single line from a neuron. Sometimes you want to add what's called an activation function. There's one activation function which is just don't do anything. That's sort of the default. But what an activation function does is it's another function. So we've got our neural network, which is a function. We've got a neuron, which is actually a function. And then within that neuron, we have a function that transforms its output. So instead of just taking the straight linear representation of the y equals mx plus b calculation we're doing here, we can run it through a function and transform it in some fashion. And this is useful because it keeps extreme values from messing with it. And so sometimes negative numbers are a little wonky when you start aggregating them. And sometimes more bigger values, if they're numerically larger, can sometimes be problematic. And so there's different solutions to that. One is to create a sigmoid. You just run that output through a sigmoid. A sigmoid is going to take the value of that function and make it equal to something that approaches 0 or approaches 1, but is never reaches those, and has a midpoint of 0.5. And so this constrains the bounds of what gets passed to the next layer in the neural network. And so that can be quite useful. You might actually want to do a variation on that using a hyperbolic tangent, where it's basically a tall sigmoid that can go from +1 to -1 and hovers around 0. Its middle point 0. And this is another common one, but by far the most common function that has been used with neural networks are what's called rectified linear units. Because in the case of the sigmoid and the tangent, the sigmoid takes it up to 1, but then to try and get further, like if you want a neuron to fire really hard, it's hard to get that to happen because you have to keep upping those weights dramatically to get, just because you keep getting closer. 1, it's that half distance to 1 each time, right? You just never quite get there. So you got to keep trying harder to get to the speed of light. Rectified linear units let you make your numbers as big as you want, but also eliminates the negative numbers. It seems to work really well for neural networks. It's a really common one. All ReLU does is it's a max function. If this number is 0 or less, it's 0. Otherwise, it's the number. So it's max x comma 0. It's either 0 or it's x, whichever is bigger. And this is by far the most commonly used one. And I've been talking about these neurons as if they had one input and one output, but actually they're not. They have lots of inputs and a single output. And so this means that they're actually not a line on a two-dimensional surface. It means that they are hyperplanes in a hyperspatial surface. So you've got, so in here we've got 3 inputs. So this is a 4-dimensional space is the thing that will divide our 3-dimensional space dividing a 4-dimensional hyperspace. And so you get a line, you get your 2-dimensional space in it. So you get 1 and 2 dimensions, or you could have 9 and 10 dimensions, So it's a hyperplane that's actually bisecting it. But the math is the same. It's still that input times the weights summed up plus the bias. And so we represent that with a little sigma function here. This is the most advanced math we're going to get to in this entire talk. So don't worry if you're not a math person. The sigma just means the sum of these two numbers multiplied together. So the sum of the weights times the inputs plus the bias. And so that's the actual function that's happening in a neuron. And then when we pull these all together, we get a nice neural network that can draw lines that are in all kinds of interesting shapes and not just straight. So you can draw interesting curved lines and have holes in it and all kinds of things. And then we can use those lines to make more interesting determinations, to predict more complex numbers, or to make more sophisticated classifications. And so that's a neural network in a nutshell here. I just heard a chat message go by. I think that might be a message from someone in chat here. I can't really see chat. That could have been work too. Hopefully that wasn't work. But yeah, so that's a neural network in general. Recurrent neural networks are a specialized version of this. A recurrent neural network has the same input layer, it has the same output layer, but it's got the same hidden layers actually, but they're configured in a different way. So here our input layers would represent, input layer represents things that are part of a series of events that are ordered. Like I mentioned earlier, there's chronology to them, or there's other meaningful significance to the order. Language would be a good example, or maybe stock prices, right? And so we're inputting those numbers as functions in the same way, but we've got a series of hidden layers, which are the same types of hidden layers we have before, but they cascade into each other. So the first hidden layer that we have here takes an input, goes to the hidden layer, it creates an output, which is passed into another hidden layer, which takes the inputs of the next item in the sequence and that previous layer's prediction. And then the next input and the next prediction. And then we can start putting the outputs. And so you see here in the middle, we have an input from two sides, and we have an output. And then here we have an input from the side and an output. And so this lets us sort of give our predictions context. It knows that this came first, and this came before that, and this came before that, or after that rather. And we have it has a memory of what's happened in the past. And so this prediction is based on previous predictions. And these sorts of structures are really good at, time series and that sort of stuff. You can configure these in a few ways. You can do a many-to-many. So you've got many inputs and many outputs. This is good for things like translation and chatbots. So you think about a translation server, we put in, English and it spits out Spanish, or we think of a chatbot, we put in a question and we get an answer. They're kind of the same problem. I gave it some words and it gives me some words back. And so here's an example of Shaggy says, look out, Scoob. And Scoob is actually a bot in this case. And Scoob's response to look out, Scoob would be roke, reggy. And so that's an example of what we might use many-to-many for. You can do a one-to-many where you have a single input and you generate multiple outputs. Most common use that I've seen for this is for captioning images. So you give it an image and it would run that through a CNN process, a convolutional neural network, to get an idea what that image might be of, and pass some of those convolutional layers into this mechanism. And then you can generate text describing what that's an image of. And if you use PowerPoint, it's using this technique to tell you when you drag an image, it'll give a little caption for it. And so in our case, we're going to use it to generate things Daphne might say. And so Daphne, we say, hey, we got Daphne, and she says something like, Jeepers, they mean business. Now, if you say Daphne, it's always going to give you this answer. So it's not the best example, but the idea is you put one input and it generates multiple outputs. And of course, there's many-to-one. This is an example where we put in, say, some text like, hey, let's split up. And then we can classify who says that. Or we could predict what word might be next in the sequence. So if you got predictive text, you say, hey, let's split. What's the next word likely to be? Or we can use sentiment analysis. And so we can put words into here and get a numeric value out of how positive or negative that was. In this example, hey, let's split up. We're going to classify that. And that's something that Fred would probably say, isn't it? So those are sort of the structures, the types of recurrent neural networks we can build, but we're actually going to build one here in this talk. We're going to use it to classify text. And what we're going to do is we're going to predict who says what. That's our problem that we stated out at the beginning of the talk. And so we're going to put in the phrase, I can't see without my glasses. And then we need to predict that that is indeed Velma who says that. So how do we do that? Well, the first problem we have is that these are words, and all the neural network stuff I've talked about so far, we haven't put words into them. We've put numbers into them. And so we need to turn our words into numbers somehow. And so to turn our words into numbers, we do what's called tokenization. And this is actually a very simple process. All we do is we take our entire corpus of text that we're using to train this model. So here we have Jeepers and All Right, Let's Go and Raggy Relp and things that different Scooby-Doo members of Mystery Inc. would say. And we're going to turn those into a simple substitution cipher. We're just going to count up all those words, and the most common word gets the number 1, and the next most common word gets the number 2, and the next most common word after that gets the number 3. And so we're just saying, for example, the word like is represented by the number 1. So we're just swapping them out. It's just like a Caesar substitution cipher, where you say the letter A is 1, and the letter B is 2, and the letter C is 3, and then you have encoded your text, kind of like we did when we were in elementary school watching Scooby-Doo. And so that's all tokenization is. We've got a specific process here where we're looking at word frequency, and the more frequent words go to the front. I think that's just because it's faster, honestly. And honestly, when it comes to doing this later in Keras, we're just saying, here's our body of text, generate my tokens for me. And so this is actually one line of code to make this happen. So once we have our tokenized corpus of text, we can then start encoding words. And so we can take the I can't see without my glasses phrase, and that gets turned into the number 10, 8, 21, 23, 4, and 3. Because if we look up I over here, it's number 10, number 8 is can't see without my glasses. You get it. It's a simple substitution cipher. And so that's how we turn our words into numbers. Now, we're not done yet. We have more that we need to do to our words. And one of the things we need to do to our words is pad them. You might notice that I've got 7 inputs here, but I've only got 6 words. And you might have noticed that I right justified them. And there's a reason for that. How do I, I know how to encode, I and can't see, but how do I encode this? How do I encode the null? Well, that's actually really simple. Null just becomes 0. That also is how we encode words that we don't recognize. If we are given a word and someone put in some goofy goober, put a SpongeBob reference into the Scooby-Doo universe. If we do that, it's not going to recognize that word, and so it's going to replace it with a 0. And that works because odds are there's enough context it can figure out what's appropriate anyhow. It doesn't really know. When you hear a word that you don't recognize, that you don't know, you can often figure out what was said anyhow, the context of the conversation. Our model will do something very similar. So the null just becomes a 0. And so we sort of pad it to the left. The left padding it's padded full of zeros. So now we have a nice, thing that's the proper width. What we do next with this word is we one-hot encode it. And all one-hot encoding is you take that array of words, of encoded words, and we turn them into a 2-dimensional array where we put 1s in the column number represented by that number. So in the case of 0, that's null, nothing gets set. In the case of 10, position 10, that would be sub-element 9 if you're using 0-based arrays, gets set to a 1, position 8 gets set to a 1, and everything else is 0. And so we've gone from having pure numbers to more of an encoded, one-hot encoded value for, this is useful for classification and that kind of stuff. Excuse me. So we've gone from encoding them with a substitution cipher to encoding them with a bunch of 1s and 0s. It looks kind of binary-like almost. Once that's done, though, we've got a really big input array that's very sparse, right? It's mostly 1s, or it's mostly 0s with an occasional 1 here. And we've got 20 words in our little sample corpus here, but a real dictionary is probably going to have 10,000 words, 20,000 words, depending on how much text you have and how much vocabulary is in there. And our sentences are probably going to be longer than 7 words. They could be 100 words long. And if we're looking at paragraphs and documents, this gets big quick. And so to take those and collapse them back down a little bit, we do what's called embedding. And so what embedding does is it takes that really wide, 10,000 wide array with a single 1 and a bunch of 0s in it, and condenses it down to a smaller array by creating a lookup table. And so we can build an embedding using Keras. It will just do it for us. And we just need to tell it the right values. But the idea here is that we go through our array, we look for the word glasses, and then we get this numeric value here instead. And so we have a one hot encoded word glasses. It's encoded with this embedding as 1201475.0. And the idea here is that these columns are sort of encoding semantics around these words. So for example, glasses has a high value, and something that was similar in meaning to glasses, like say spectacles or goggles, would have a correspondingly high number there. Whereas if there's numbers that are low value next to each other, they don't have a correspondingly high meaning to each other. So it's a way of doing it. It's a little bit of magic, and I don't fully understand how it works in excruciating detail. I don't know the algorithm beneath it. I know the intention of what's being built here, and I know how to make it work with Keras. But there is still a little bit of mystery here. I still have a depth to explore, so that so I can see that the ghost here is actually just a man in a mask. But once we've gone through all these processes, what we're really putting in is not these words, but these numbers. And so null is a bunch of zeros. I is this particular numbers from those word embeddings. And so each of these embeddings represents a word. And so now we're passing in our sentence. And I mentioned that we have it's right justified for a reason. And that reason is what's called the vanishing gradient problem. Oh, I missed a bit here. Sorry, I skipped a slide. Like I skipped slides here, and I got all confused. So those are our inputs, but our outputs is not Velma, right? It also needs to be a number of some sort. And so that output from our recurrent neural network is not Velma. It's an array of numbers as well. It's a tensor of numbers, a one-dimensional tensor. And in here, we've got 5 numbers, 01, 02, 11, 0.3, or 0.03, and 0.83. And you'll notice these add up to 100%. And so we can think of these as percentages. And all these is the different members of Mystery Incorporated. So we've got Daphne, Fred, Scooby, Shaggy, and Velma. And it's giving us a percentage guess on how likely it is that particular person that said it. And so here we got a 0.83 saying that Velma is probably the one that can't see without her glasses. And there is a weakness in recurrent neural networks, which is what's called the vanishing gradient problem. The vanishing gradient problem is that because this prediction being made by this node right here is 50% the last word I put in and 50% the entire context. And so that entire context then is 50% the word my and 50% every context before that. And what it means is that words in the past, or words that are earlier in the order, things earlier in the sequence, are less important than things that are late in the sequence. And so if I could say I can't see without my glasses, the my glasses is more of what the model is learning from than the I can't see. And so you'll see here as I do some examples, if I put in like Scoob, I can't see without my glasses, it's going to guess Velma, even though like Scoob is something Shaggy starts all his sentences with, it seems. And so this is the vanishing gradient problem. The newer data is more important than the older data. And there's some workarounds for that. I'll leave those as an exercise for you to go research on your own. There's long short-term memory and gated recurrent units, which can address this in a couple of different ways. But that's recurrent neural networks in about 15 minutes, maybe. I kind of rushed through that quite a bit. But go check this stuff out on your own as well. It's really quite fascinating. Keras is the tool that we're going to use to build our recurrent neural network. Keras is a domain-specific language that simplifies writing neural networks. It lets you focus on your neural network and not on any mathematics. And so it's a great tool for developers who want to play around with building some models, but don't want the complexity that comes with something like TensorFlow. It's written for Python developers specifically. And it actually is part of TensorFlow. Wasn't originally, but it is now. And so it exports TensorFlow models that you can use. Here's some actual code on doing this. Here we're defining a new model called sequential. It's called sequential because it's got this layer followed by this layer followed by this layer. And we're just going to create a simple network here that is a fully connected network of the variety I showed at the beginning. We can add some layers here. We're adding a dense layer with 5 neurons. A dense layer means it's a fully connected layer. It takes all the values in and puts all the values out. We're going to use the ReLU activation function. That'd be the max 0, x. And we're going to say that we are expecting 4 inputs into this layer. The next layer is defined as being a dense layer with 5 neurons as well, activation ReLU, just like the previous layer, but it doesn't have an input. And then our output layer is, again, a dense layer, take inputs from everything. And its activation is softmax instead of ReLU. And softmax gives you that 0 to 1 range. It adds up the outputs of all these neurons, makes them so that they can be expressed as a percentage. We will then compile that, calling model.compile. We'll use an optimizer of Atom. Atom is a stochastic gradient descent variation that figures out what the values for the weights and the biases should be inside of the network. The loss function will tell us how wrong we are. And between the optimizer and the loss, we're able to figure out where the errors are at in the neural network and update the weights and biases to reflect that. And then we can spit out some metrics here that represent our accuracy. We want our loss function, of course, we want that to be a nice low number, and we want our accuracy to be nice and high. Once we've got that, we call model.fit, pass in our training data, X for the features and Y for the labels. We give it a batch size, which says, look at 20 values, run them through, get value results out of those, run the optimizer and the loss function, do it again, do it again, do it again. Go through our entire data set 10 times, which is what epochs is for. Once we have a model, we can evaluate it against our test data, passing in our features and labels, and it will tell us how accurate it was in reality, as opposed to what model fit says. It'll evaluate our model. And then once we have it, we can start making predictions by passing in values for X. And so this is not a lot of code, actually. Pretty simple. A recurrent neural network is not much more complicated. It's got different types of layers in it, though. So here we're creating a sequential model again, but instead of adding just a bunch of dense layers and that's it, we add different types of layers. And so we add an embedding layer whose purpose is to go through that whole embedding process that we showed earlier, where we take our words and we turn them into the one-hot encoded and then make that a more condensed version of that. And so we add an embedding and we tell it how many words in our vocabulary, that's how many things are going to go into the embedding. And then the output dimensions would be how many columns we want in that embedding and how long our words are. And those are all the things that it needs to build that embedding layer, and then it will just do it for you. And then we call, we say we want to add a simple RNN, so that creates our recurrent neural network. And it needs to know the number of embedding columns, because those embeddings are going to be the inputs coming into it. And then we can add an output to it as well, a dense activation layer, just like we did before. This would be our classification layer. I have highlighted versions of those things I just said. I think it's time for a demo. I've actually built some code to do this. So let's take a look at it. So here's the Scooby-Doo data that I was showing you earlier here. Here's the who says it, Shaggy Rogers. Yes, his last name is Rogers. And Scooby-Doo and Velma Dinkley and Fred. What's Fred's last name? I can't remember. Anyhow, it doesn't matter. And then we've got our little build model script. And this is a lot of the code that I really just talked about. And if we go through here, we can see that I'm using pandas to pull some data in. I'm pulling out the features and the labels from my little simple CSV file, splitting them up. And then here I'm encoding the character names. Fred Jones. Jones is Fred's last name. And so that we get out numbers indexes 0 to 4 for Daphne all the way up through Velma. So we're taking these names and we're turning them into numbers. And so we do that by creating a label encoder, handing them our list of all the names that are in our data set, and then it will just create a list of all the classes. And we can actually see what that looks like as a JSON file right here. Very complex JSON file there. And then we just save that out, and we go ahead and encode all of our labels so that now instead of being words, they are numbers that the model can deal with. And then we one-hot encode those as well by calling toCategorical here. This is our tokenizer, where we take our lines from Scooby-Doo and turn them into numbers as well. We're going to go ahead and give it a vocabulary of 10,000 words. None of the lines have more than 150 words in them. And so we create a tokenizer, giving it the max vocabulary. And we just tell it, hey, here's our text, tokenize it. Count them all up, figure out which one's number one, in the number one position, give it its number one, give it the biggest word. And you end up with something that looks like this. So if we look at here, the most common word is the, unsurprising. And the least common word is eyeballs. And so this is our little dictionary. And then we can convert all of our text to sequences and pad them with empty spaces and tokenize them. And now instead of having those words as arrays, we have arrays of numbers representing those words. Then we split our test and train data out. We take 20% and set it aside to validate our model at the end and use 80% of it to train it. Here, we're going to go ahead and build our word embeddings. This is the same code we saw on the slides, just a little bit wider to represent something a little more real. Then we add our embedding layer. We add our simple RNN. We have our output. We compile our model, print out a little summary, model.fit, model.evaluate, and then we run some test predictions through it. So let's see this actually do a thing. So we'll say Python build model. And so I hit enter here, and there's going to be a little bit of a pause, and there we go. It's tearing through it. You see our accuracy starts out really crappy, but then it improves. Our loss function gets smaller as we go. This is all great. And then we get some of our predictions here. So let's take a look at this a little more closely. We can see here that the accuracy looks great as we're training. And then as soon as we compare it against our control data, the data we set aside, we realize our accuracy is actually quite atrocious and our loss is terrible. And this means that our model's overfit. We're going to use it anyhow, but our model is overfit. This is why, as a developer, you should always pair yourself with a data scientist when you're doing this kind of work. Here's some of our predictions. The word Jinkies is turned into this sequence, and we see that that's most likely Daphne Blake. Or no, sorry, Velma Dinkley here at 67.734%. Like Hang On Scoob is likely said by Shaggy Rogers at 0.99 or 99%. And Roque Raggy is probably Scoob at 92%. So we built a model, we did some basic predictions. Hooray, it works. So I'm going to talk a little bit about Redis API, and I know I'm running out of time here, so I'm going to go a little bit quick on the Redis stuff here. RedisAI is a module, which is something that can extend the capabilities of Redis. You can take Redis and add a module, and now Redis has new capabilities. This adds AI features to Redis. In effect, turns Redis into a model server. So you can deploy your models to Redis and then make predictions there. And which of course provides fast and easy integrations. Lots of people are using Redis. There's 1 million clients in 1 million languages. For Redis, you can easily talk to Redis. This sort of opens up, and this is actually the thing I think is really cool, is that it opens up your models to any platform. And so you've got some obscure platform like Elixir that you're using. You don't have to constrain your developers to use a particular tech stack. They can, as long as they can talk to Redis, they can talk to the model. It also supports multiple backends. And so if you're doing your models in TensorFlow, or you're doing your models in PyTorch, or if you're using Onyx, which is a sort of a general purpose model platform, which there's lots of tools to convert other models to Onyx models. It means your data science team can kind of pick whichever stack they want, and that your technology, your app dev team can pick whatever stack they want. And bringing those together, it gives a nice layer of abstraction for building out applications that need to have models. RedisAI introduces two new types: the tensor, which are those multi-dimensional arrays that are used all over machine learning, and models. And the way it works is pretty simple. We load a model using the AI.modelSet command. We load a tensor using the AI.TensorSet command. We actually run the model using the AI model run command and telling it, use this tensor as your input and write your output to this tensor. And then we read the outputs using AI.TensorGet. And so load some data, run the model, read the data. It's that simple. Here's the commands. I'm going to skip over these really quick because I'm getting a little short on time here. The key thing here is this is setting and getting a tensor. It's sort of a dense command, but it's actually not very complicated. The main thing here is you have a shape, which is the shape of your tensor, and then the values that make up your tensor. And then the tensors go in a key in Redis. And getting a tensor, you just say, I want to get that key, and say, give me the values and give me the metadata. Setting a model is a little more sophisticated, but it's, again, just a command. I'm using Redis CLI with the -x command, and that takes things from standard in and pipes that into the rest of that the model set command. So you don't have to type in a bunch of binary data. And to run a model, you literally just say, here's the key containing the model, here's the input tensors and the output tensors, and it'll do it. Putting it all together, we end up with a little application where we type in rokraggy. We hand it off to Redis. Redis hands it off to RedisAI. RedisAI hands it off to the model makes a prediction, it comes back, and we learn that that was said by Scooby-Doo. So let's look at our second demo here, where I've actually built a thing that hosts the model. So I'm starting up a little NPM server. This is a JavaScript server. I should totally have a Flask version of this, but I don't. And then I got a little web client here, Python mht.server. And what I've done is I've just written a bunch of JavaScript code to talk to RedisAI, to talk to Redis to use the models that I've made. And I'm not going to go into the details of the JavaScript code because this is a Python conference. You don't want to see JavaScript code, and I don't have enough time. So, but this gives us this fun little application here. And we can enter a line from Scooby-Doo like rut-row. How do you spell rut-row? I don't know how to spell rut-row raggy. There we go. Hit enter, and we can see that that was said by Scooby-Doo. And if we say, I can't see without my glasses, that was from Velma. Like, hang on, Scoob. Who says that? Shaggy says that. And so this is going through RedisAI. If we go and look at the console here, we can see that it's actually spitting out the classifications. And so the first one was fairly certain that was Scooby, fairly certain that was Velma, fairly certain that was Shaggy. So cool. It's kind of fun, isn't it? So that was a lot kind of quickly. We covered neural networks in a fair bit of detail, recurrent neural networks as well. And we went into Keras to learn how we can fairly easily build these neural networks without even really having to understand in detail how they work, which is both powerful and dangerous. And so I always want to include the caveat that you want to work with a data scientist if you're a developer, because I made a model that looked really good, but it turned out it was overfit, but it does identify all their catchphrases, which makes for a fun demo, right? So check out Keras. Keras is really cool. And then we talked a little bit about RedisAI and how we can use that to host our models. Here's a bunch of links for all this kind of stuff. The main link that you're going to care about is RedisAI, if you want to use RedisAI, but is the one with the code in the slides if you want to reproduce my little exercise here, you can go out and hit that there. I, of course, work for Redis Labs, and so we've got some stuff we'd like to check out. Check out the Redis Discord server. I'm on there all the time, so if you want to message me anything. We got free courses on Redis University, and I got some Redis University videos out on YouTube as well, where I talk about Redis AI and lots of other fun stuff. Should have a one on writing Discord bots here coming out really soon. And here's a little QR code that will take you to that URL. I promise you that it will take you to that URL, and this QR code will not give you up, nor will it let you down or run around or hurt you or anything like that. So you can totally trust it. My name is Guy Royse, and thanks.